So currently, visual impairment affects 2.2 billion people, leading to an economic loss of over $3 trillion. And yet, despite this, 1 billion of these cases have yet to be addressed, and this is due to current lack of diagnostic technology, as well as critical lack in refractive technology. Now, the biggest cause of this is due to retinal diseases, and currently retinal diseases are being underdiagnosed, and the current diagnostic process is reliant on manual diagnosis. So when I say manual diagnosis, the two critical issues with manual diagnosis are, one, it's very time-consuming for physicians to go patient by patient to diagnose them, and then two, it's prone to variability between different physicians. So this is where AI comes in, and where AI can help enhance diagnosis. But AI currently has three critical limitations. The first one is generalizability. So current AI models use optical coherence tomography scans, OCT scans, in order to visually diagnose patients with retinal diseases. But these OCT machines that generate the scans produce speckle, which is a noise-like artifact that appears as white dots across the screen that come from light that comes from the OCT machine bouncing off various retinal microstructures. So this obscures certain pathological features and makes it harder for AI models to diagnose. But because it comes from the physics of how light bounces off microstructures, we should use it as a diagnostic signal, which is something that my research addressed. The second major issue is the lack of personalized analysis. That being, there is a lack of severity estimation and progression analysis over time, which is critical for physicians to understand and diagnose patients, as well as making more effective treatments. The final issue is interpretability. Interpretability is an issue because physicians provide an input and they receive an output, but they have no reasoning to understand how did the model come to certain decisions, and that reduces trust in these AI models. So what I did was I developed a tri-framework CESS to address each of these limitations. The first one is the Speckle-Aware Dynamic Vision Transformer, SADVT, which actually uses speckle as a diagnostic feature to enhance the diagnosis and increase accuracy. So this model achieved a 96.9% accuracy across 6 different data sets, showing that it is one of the strongest models in the world for accurate retinal disease diagnosis across various different imaging conditions. The second, innovation that was done in this research was the development of the Severity Estimation and Personalized Analysis Framework, SEPIA. And what this model does is it takes all the images and calculates the normal class, what a healthy patient would look like on average, and then calculates the Euclidean distance of that image, of an image that it receives, to that normal class centroid, and provides a quartile severity label, as well as it provides a percent deviation score for quantitative metric over time of severity, allowing physicians to microanalyze how patients respond to various different treatments. Finally, the last innovation that I developed was the CRAFT framework, Clinical Reasoning and Analysis Framework for Trust. And what this did is it used 3 different separate models, T-distributed stochastic neighbor embeddings. It used GPT-5 and SwinUnet to provide graphical, textual, and visual interpretability. So provide this interpretability framework that allows it to enhance the interpretability. And it produced a dimensionality reduction graph for the TSNE visualization, which allows physicians to understand how the model understood the various different clinical features. The second thing with the GPT-5 model, it produced an effective patient report to analyze the different biomarkers that it found and provide a clinical summary, as well as understand the different retinal layers, and cohesively analyze all these into a single patient report in order for physicians to verify the model's results. And then finally, what the model did was provide a segmented retinal image that allows physicians to clearly understand the different biomarkers, where they might lie in the separate different retinal layers. So overall, what my model did was provide generalizability, accuracy, interpretability, and severity and progression analysis, which are all 4 areas which are currently lacking in the diagnostic process. You can come and see my poster over there for more information. Thank you.